Um, and pedigrees, if you look at it, it looks a lot of like family trees. If you ever done a family tree of your family, including your grandfathers, your uncles, your aunts, your cousins, yourself, your parents, it looks a lot like that because it is exactly like that. The only thing we add is something that we learned for the past weeks, which is phenotypes. So in this family tree, not only we add every person in your family, but we also look at one characteristic at a time. So let's say we're looking at hair color. We're looking at who in your family has brown color in their hair. In this case, whoever has that brown color, we will put a little shade of, in this case, blue, but it could also be gray. It could be any color really, but we would highlight which people in your family have that phenotype. So again, for those of you who are asking what a pedigree is, it's a family tree that looks for one characteristic at a time, and whatever people have that characteristic, that phenotype, is gonna be shown with a little color. Usually gray, usually black, but you could do it red, blue. The color doesn't matter. What we're looking at is who has that characteristic in your family. A lot of you still discussing about the NASA website. All right, let's get focused on. Now it keeps going. It explains a couple more times what can we see in a pedigree 3. And let's keep it simple, guys. I know this is a lot of text, this is a lot of information, but just keep in mind that the reason it says can we guess their genotype is because a lot of times looking at phenotypes, we can make guesses or we can make inference of what their genotype is. Like we could say if this person is heterozygous, if this person is homozygous, and it's going to be a little more clear in a second. But the only reason we talk about genotypes when we look at family trees is because we can guess what their genotype is based on their phenotype. Obviously, if you look at these children right here, we are not 100% sure if they're homozygous dominant or if they're heterozygous. So it's a wild guess, but what we're looking at in a pedigree tree is their phenotype, if they have the characteristic or not. All right. So this is another question we have in the lesson. And then we go into jumping characteristics. So anybody in the chat can tell me what a jumping characteristic is. Do you remember about carriers? If you know right answer, so you can unmute yourself and you can tell us what a carrier is. Let's see. Skip generations. Yeah, Ben, do you want to unmute yourself for a second? Can you tell us what you remember about carriers or skipping generations? Ben? If you can unmute yourself. Let me see if I have sound. Yeah, I have sound. Oh, they skip generations. Let's see. Okay, Christopher, you can unmute yourself. What do you remember about skipping generations? Thank you, Ben.
So what I remember about skipping generations is that when it's either carried by probably a heterozygous or maybe a dot or a recessive allele, or it could be like a recessive trait maybe. Or if not those, it just means that it's being carried by one of those. But yeah, I feel like it's mostly being carried by a recessive trait.
Yes, thank you. That was amazing. Thank you so much. So you were mostly right, but you need to make sure, you said it in the beginning, it's a heterozygous person. So the only person, and that was a question in the quiz, which a lot of people got a little wrong, is that when we talk about carriers, they are only heterozygous people. I know we can say, oh, well, maybe sometimes homozygous, recessive or homozygous dominant people might be carriers. No, heterozygous people are the only people who can be carriers. And this is the reason why. So if we look at this tree, the people who are half blue, half red are obviously heterozygous. Remember, hetero means different. So they obviously have one allele for one characteristic and one allele for another characteristic. But if we look closer, the reason they are called carriers is because they can take that recessive allele and pass it to their kids. So in this case, this person right here, who is half blue, half red, if you were to look at them, you would only see the dominant allele in their body. You would only see the dominant phenotype, but they are carrying that recessive allele in their genes, and they're able to pass it down. Look at these grandparents. Both of these grandparents were heterozygous, also known as carriers. Thank you, Christopher and Ben. But they are able to pass down those recessive alleles and have a kid who doesn't look like the parents. So both parents, they show their blue genotype, the blue phenotype in their bodies. They might be, let's say the blue phenotype is blonde hair, and the red allele is brown hair. So both grandparents have blonde hair because they have the phenotype, which is the dominant phenotype, but they're able to have a kid with brown hair because they pass that recessive allele. All right, so let me just make sure, you know, heterozygous people are the only people who can be called carriers, and they're called carriers because they carry that gene, that allele, recessive allele, to a person who has recessive characteristic. Now, this is going to make it even more simpler. So there's a practice right here, and it asks us for a couple of conditions. The first one is attached earlobe. It asks us if it's recessive and dominant. The second one is hemophilia, which is a disease that causes a lot of people to bleed excessively. Hemophilia. And there is another one, which is Huntington's disease, if you remember for a couple of weeks ago. So every one of these conditions is going to ask us if they're recessive or dominant. And let me show you a trick. So you're lucky that you guys are here in the check-in, so I can basically tell you the really quick shortcut that it's going to take you 1 second to solve. So let me just make it bigger. 1 second. So we look at here at hemophilia, and we want to know if this pedigree, if this characteristic is recessive or dominant. We always want to know if that characteristic is recessive or dominant just by looking at this pedigree. And let me tell you how to do that. All right, so we have hemophilia right here. We have the pedigree. First thing we know is that people who are shaded is because they have that characteristic. In this case, people who are shaded, they have hemophilia, which is a disease. So terrible, terrible disease. But the people who are shaded have that disease. Now, how do we know if it's a recessive disease or it's a dominant disease? By the way, a recessive disease means that you need two recessive alleles in order to have that disease. So remember, recessive disease means that people who have that disease or that characteristic, like red hair, blue eyes, whatever recessive characteristics you're talking about, they need two recessive alleles in order to have that disease. All right. So how do we know if hemophilia is a recessive or maybe is a dominant characteristic? So if it's a dominant characteristic, we would see something like this, maybe a heterozygous person or a homozygous dominant person. Oh. So we need to decide if this characteristic is recessive or if it is dominant, okay? And the way we go about that is just by looking if it jumps a generation or not. So because it jumps a generation here, so we see that the grandparents have the disease, the kids don't have the disease, but then the grandkids have the disease. That means it's jumping a generation. So you know already that it's a recessive characteristic because it's jumping one, and these are these parents right here are probably what? If the grandparents have the characteristic and the grandkids are have the characteristic, what do you think the parents are? What can you assume of the parents in terms of homozygous or heterozygous? If somebody wants to write in the chat, or if they want to mute themselves, let me see what the chat says. So what can you deduce of the parents if you see they are carriers, right? Yep. Tyler, you want to unmute yourself? How do you know the parents are carriers?
I know they're carriers because if they were like homozygous dominant, then their child, if they were, okay, I know they're carriers because if they were like homozygous dominant, then they wouldn't have any child with hemophilia. And if they were both recessive, then all their children would have hemophilia. But if they're carriers, then there's a less percentage chance that their child will have hemophilia, but there's still a chance.
Yep. Perfect. Thank you. So if we were gonna look at the genotype of each one of them, we would see exactly what Tyler said. We would see that the kids are probably heterozygous, so that means that they have one disease for the allele. One allele for the disease, and the second parent would probably also has to have another allele for the disease, because we know that the kid has the disease. So this kid right here needs 2 copies of the allele. So one parent is going to be heterozygous because he had the gene from the grandparent, and the other adult probably in case this is the husband, we know because it's a square shape. Remember, squares are men, females are circles. Both of them are heterozygous, and that's how we're able to get this. So if a question asks, do you think this pedigree is heterozygous, this characteristic is recessive or dominant, you're gonna see if it skips a generation. If it skips a generation, you know that it's probably a recessive allele, since you need 2 copies of a recessive allele to get that disease or the characteristic. And if in that case we have heterozygous parents. So let me just say that once again. If it asks if it's dominant or recessive, the characteristic, you're gonna look if it skips a generation. If it skips a generation, that means it's most likely a recessive characteristic. Let me show you how a dominant characteristic looks. Give me 1 second. Oh, I'm gonna close this actually. So this is what a dominant characteristic would look like. A dominant characteristic, for those of you who haven't done the assignment yet, a dominant characteristic is gonna look a lot like this. And it means that if your parent has, I'm sorry, can we just make it bigger? Okay, so a dominant characteristic, it looks something like this. And there is a direct inheritance of the characteristic. So this is Huntington's disease, and we know it's dominant because we don't see in any case that the disease is skipping our generation. Let me just show you bigger right here. So the grandparents, one of the grandparents have the disease. The parent generation has the disease as well. And the grandkids generation also has the disease as well. So there is no instance whatsoever in which the disease is jumping any generation. Every generation in this pedigree has the disease. So because it's not jumping any generation, we know this characteristic is dominant, right? So in this case, let's just guess the alleles. So I'm gonna say this grandparent is, let me make it a different letter because this letter is impossible to write. Let me say P. All right, so large P is the Huntington disease. This parent could be, let's say, heterozygous. We don't care. This grandparent could be also, let's just say, is heterozygous as well. So in that case, you will have the disease. Anyway, the parents could be also, could be heterozygous as well. And then we will have kids who have 1 copy of the allele. Actually, let's make this grandparent recessive. All right, so let's make this grandparent homozygous recessive. That means that they don't have the disease, but the kids, since one of the grandparents have the allele, just by getting 1 allele of the disease, they're immediately going to have that disease. All right, so dominant diseases are more common because you only need 1 copy of the disease. That's the reason recessive disease are not that common, because you need 2 copies of the disease to have it. Dominant disease are more common because you only need 1 allele. So you could have dominant, or you could have heterozygous people having that disease.